Hey guys. Can anyone hear me? Yeah. Good. Sorry about this last minute disaster. We'll wait for everyone to join in. I'm very sorry about this. The link I forwarded out wasn't working, so should be good now, hopefully. At least I'm recording it this time as well, so should be good. How are you guys going? Everything good? You good? I'm good too. Just very stressed after having the meeting link not work, panicking. So we'll run a little bit longer just to make sure we cover everything, if that's okay. Okay, we've got 17 participants. That's great. Everyone found the link, okay? Really sorry about that. That was a bit of a disaster, everyone. Oh, well, we're learning. It's all new. I'll just wait a tiny bit longer just because I only just sent the link. Hopefully everyone's watching Blackboard and they can find out what's going on. We'll give it a little bit more time. How's everyone finding the assignment so far? Easy, hard? No one's brave. Question 5. I can't remember which one question 5 is. All right, I'll look at it quickly while we wait for everyone to stand up. Yeah. Don't be afraid. It's good, good to try. Yeah, that one's a bit tricky. We'll cover a bit of that stuff today. So a little bit ahead of where you guys are. So lectures will catch up finally. But like it says, it gives partial credit for finding examples. If you want a big hint, I'd look up quadratic surfaces. This is an example of one of those. You'll see some plots that look a bit like it today in the lecture. So it should be good. Hopefully that will help. Okay, we've got 21. I can feel like I'm allowed to get started now. Yeah, quadratic surfaces, they're the ones. So today, we are doing relations and functions, section 4, and it's a big section, and I already wasted some of you guys' time, so I'm very sorry. So we've got a lot to get through. A lot of this stuff's conceptual stuff. There's lots of examples, but the examples in this one, luckily for this one, they're sort of easy. Some of the examples are a bit tricky, but really this one's about conceptual stuff. We really want to go through making sure you understand relations and then functions from that. There's a couple of sections. First off, we're going to do relations. Then we're going to talk about a special sort of relation called an equivalence relation. We're going to go into functions, examples of functions, but we'll probably go through those fairly quickly because there's stuff you probably have seen in your education before. Good thing is functions are so important that they're the thing you think of when you think of maths. So we're sort of snuck up on it for coming from discrete maths. We've gone very, very low level from set theory and we go, special sort of sets. We can look at relations and then we can go back to things you're familiar with functions. And then I guess the next step on when you're with Hamid will be going to calculus, which actually helps you answer question 5 as well. You don't need it to answer question 5. Yeah, so then we'll talk about composition of functions and this special thing about one-to-one, onto, and what they really mean. Get both of them together about inverse functions. Then I think the last bit's multivariate functions. That's the big outline of what we're going to do today. Again, I'll just go through the reader. please, if you've got any questions, let me know. I'll just try and find my notes and share that with you guys. So hope that's big enough for you guys to see again. Again, we'll just go through the reader together. If you've got any questions, shout out, because you know you've got time with a real human. Important in these times to actually be able to ask questions if you don't understand. Okay, so last time was logic, proofs. Before that, well, feels like another lifetime ago, in another century, we were looking at sets. So we're sort of coming back round to sets, and you can some of these sets in this bit. So hopefully you start to see some connections as we go through. So relations are really simple. So simple idea, but make sure I got the right color here. So if I squiggle all over this page, you guys can see it. I'm going to make my text box a bit bigger. Okay. Okay, so remember this guy, the Cartesian product. I actually have my pen. The Cartesian product is what we're going to talk about, where sometimes you say cross product, product space, blah, blah, blah. This set of all the elements of A and all the elements of B together. So we have a special thing we're going to call a relation, binary relation. You can have more than binary, but we're building up to things here. Is just any subset of this guy. Very simple. So, yeah, it's almost trivially simple. It's just a subset of this product space. So all these tuples are, hopefully you can see into the future, but and see where this is going with univariate functions. But yeah, we've just got product space, x's and y's, and it's got some relation. And we say if it's an element of that, it's x is related to y by r. So r is this relation. So if they're both an element of this subset. So there's some funky notation. You'll see not related to. I don't think I ever seen that one variation very often, but this guy, not an element. You should be all familiar with those symbols now. Or yeah, relation defaults to binary relation when the context is clear. It can be, you know, because you can have n tuples instead of just this tuple here with two elements, AB. Write lines under it again. I don't mind if other people close their microphones. That's fine. Because that's a new question to everyone. In the chat, we just had Ningwang ask if we can mute the mics. I hope I've got no feedback on mine at the moment. I can probably turn my mic up a little bit too. A little quiet. Is that any better?
No.
Someone's eating noodles. Okay. Oh no, it's dinner time. Yeah, so I don't know if I have control. I might have actually. You'll probably see a bit more detail. Sorry guys, I'll just try and see the controls, see if I can actually do it. No, doesn't look like I have that much power. Sorry guys. Oh, well, we'll keep going. I'm just trying to be quiet. So, okay, so Japanese noodles. Anyway, okay, so, okay, cool, thanks guys. So you see R is really common for the relation, but you'll also see rho, sigma, and tau. Saying here for notation. Notation is really important. Okay, we've got a really simple example here. Okay, let's see. We might have to skip through a lot of the examples unless it's not clear. So you can define a relation. So like this guy with A and B, we might do this 77 really quickly. We've got 0 to 4, 1, 2, 3, 4. So I might try my best to draw this guy. And we've got the relationship in there. It's in this subset if x is less than or equal to y. So I'll try and draw it. It's going to be a bit sketchy with my fantastic set up here. So we can do this as a plot. I really apologize for my drawing skills, everybody. So we got, these will be the guys A. I'm going to use text for the next one. Sorry, that's atrocious. That's B. Try and make this fast. A lot to go through. Okay, so we've got A and B, and we've got these elements in B has 1, 2, 3, 4. So remember, we're doing this product space. So 0, 2, 4. Okay, so remember, each one of these is a tuple. So you're going to have, I'll change to a red dot. I want it on the text, I want it on this guy. So we're going to have this guy, need a bigger dot so you guys can actually see what I'm drawing. So we've got 0, 1, 0, 2, sorry, AB. So it's going to be 2, 1, 4, 1. So each of these guys, so you know, this is, each one of these is an element of this product space. And as we said, a relation is just a subset of this guy. And we've said you're an element of the subset if X is less than or equal to Y. So leadingly drawn it on this X-axis here. So if we're going to go for 0, is 0 less than 1? Yes. So this is an element of the subset. Is 2 less than 1? No. So that's not, 4 is not less than 1. So we got this guy. I think it was less than or equal to. So you're going to have this guy. And blah, blah, blah. Should be able to go quickly. This one is 3 less than 2. So X is less than Y. So that's that one, that one. 4 is not less than 3. So it's just this guy up here. So the yellow is probably really bad color, but anyway, hope you guys get the impression. So that subset is the relation. So hopefully that's super clear. It's very simple. A little bit interesting to work out why we care about this. It's really because we're sneaking up on functions. So go back to the notes. We've got some questions about there. Is not 2 because blah, blah, blah. We just basically wrote out every element of the relation in that picture. Pretty simple. So I'm conscious of speed and your time. So have a look. So basically, I'm going to skip examples. If you have questions, please ask me. I'd encourage you to go through these on your own. But as I said, a lot of this stuff's going to be really conceptual stuff. We'll skip through relations. Just the idea of a relation is probably more important at the moment. So back to concepts. This guy's really important. So there's some big words here, but it's going to come back, and it's a really good way to think about this stuff. So this one scare anyone? If I say a directed bipartite graph, is that an expression you've heard of before? Anyone? Take it as a no.
No, Paul.
No? Okay, cool. I heard some. That's nice. Okay, so directed bipartite graph. So it's a big word. It's, this one's another one where you help. It's basically drawing pictures for this stuff. So we'll go down. So we can think of two sets. I want this guy black. So we've got A, B. I'm going to try my best at drawing it. These guys have got stuff in them. 1, 2, 3, and 6. I'll draw a circle around that in a second. And we've got this one. It's got A, B, C, D. So we can think of a relation as this general thing where we're going from elements of A to elements of B, and each one of these is one of these tuples. So say 1 goes to A, 1 goes to C. I'm not drawing the one above, I'm just drawing a random one here. 3 goes to D. So bipartite, so a graph is a collection of nodes and vertices. Bipartite means you can separate them out into 2 clumps and the edges are all going one way. So that's this guy. So the relations here would be 1A, 1C is a tuple, 3D is a tuple. And this is your set A, this is your set B, the product space of all these ones. So again, this is a subset of all the relations of, sorry, a subset of the product space is the relation. So when you see this directed bipartite graph, it's one of these pictures where each of one of these goes with 1, 3, 6 is a node, A, B, C, D. And you're drawing arrows to represent the relation. And humans, being very visual creatures, I know I am, really helpful to think about this way. So that big scary word, directed bipartite graph, is just one of these pictures. You've probably seen one of them before, maybe, maybe not. Really useful for when we go through some of this stuff about, particularly when we're talking about equivalence relations. So, yeah, so I think I just drew what they said there in words. Partite sets for the vertices of G are A and B. So that's the big blobs. You've got a bunch of vertices A, B, and there's an arc, a directed edge from A to B. So in general, graphs, really useful mathematical object. If you're doing programming, you'll come across graphs all the time. You can have undirected graphs. General graph isn't bipartite. You can't split the nodes like that. So it's a particular type of graph. So where you can split it into 2 clumps, all the arrows go from one side to the other side. It's actually really useful when that happens when you have graphs. Okay, so examples again. Okay, cool. So now we're jumping ahead. So this is really the next section. So I'll say this really quickly. So a function from A to B is a relation from the set to A to B. So relations are really general. Functions are a particular type, a subset of relations, and they have a really useful property. So for every, now these are really important. I'm going to say them again later on as well, because this is the definition of a function. So for all, so this guy, for all, really note that. So that's that one we were talking about last time. For all x in A, there exists some y such that xy is an element of f. And this one is, these are the two things together. So if x, y, and e is an element of f and this, then y equals z. So saying this out loud. This one in particular. So for all y and z element of B, element of f, then y equals z. So this is, the equality is really important here. So this is, we'll go over this again, but just so you know, function, takeaway message for the moment is relations are super general, but subsets of a product space. Functions are a particular subset of that with this property that everyone in the A maps to something on the other side, and you don't map to 2 is pretty much what it's going to say. You only map to one thing on the other side. Has a special notation. Okay, so that's function. We're going to go back to that again. Don't worry about functions too much at the moment. It's just this idea of relations. Okay, we've got this guy too. So this, it's a bit hard to see all the stuff in there. So we've got this other definition. So I'm really sorry this lecture is going to be a bit dry with lots and lots of definitions. So you got to do them though for getting the concepts. There's a few here that are really important. This one is really important. Inverse relation, and it's super simple. The inverse relation, if we were looking at this guy, I'll go back to my bad picture. So if we're looking at this one, the inverse relationship, all you do is you delete the arrow and flip it around and point it back the other way. So A points to 1 instead of 1 pointing to A, C points to 1 instead of 1 pointing to C, D points to 3. So you can see that as a formula back in the notes. So the inverse relationship here is just flipping it around. It goes from, it's in the product space of B cross A. And all you do is you flip the order of the tuple. And that's, if you're drawing a picture, you flip the direction the arrow goes. So inverse relations are really good. Inverse functions are even better. So that's something we'll talk about later as well. Okay, so this will help, this definition here of inverse relation. We're going to talk about that with some of the equivalence relations properties stuff in a bit. So more. So sometimes, go for another one here. A binary relation on a set. So we're going from A and across to B. A lot of times you're interested in going from A to A. For what we're doing, you're really going to be going from, sorry, it's not working for me. You're going to be going from the reals to the reals is really commonly the two sets you're going to be doing, like normal functions, you're going to be going R to R. So that's got a special name because it's so important. It's a binary relation on a set. So that's why we've got the all caps here. If it's on a set, we'll talk about this a bit more. So if a binary relation's on a set A, we can interpret A using a directed graph again with the vertex at A instead of using a bipartite graph. So again, so this time we're not going from two clumps of vertices, we're going to vertex to vertex. And we'll show you this when we're talking about the reflexive and transitive properties and symmetry properties. Yeah, so again, you draw an arc if there's an element of the relation. Okay, and if you have XR, then in a directed graph, we'll have a loop onto the vertex X. Show you a picture of this in a second. Right now, actually. So, yeah, I was actually having a good think about how to explain this stuff to you guys. It's a little bit, this is more like how mathematicians think about things. So it's a really good experience for you guys to see. What we're building up to here is this special result about equivalence relations, they're called. I don't know if you've read ahead in the notes already so far, but got this really sort of magical property about that relates set partitions of sets to relations and the properties of the relation. Can seem really exotic. I'll try and give an example of where it's important. I might fail, but we'll see. So we've got these three properties that we care about. There's more properties you can define about relations, but these three are sort of special. So reflexive. So for all x in A, we have this relationship, XRX. So that basically means that of the tuples, you're going to have, if you've got a set, you set A equals A, B, C, in the relation, which is a subset of A cross A, you're always going to have A, B, B, etc., etc. That's what this one means. So this one is always an element of the relation. If all these guys are in here, it's called a reflexive relation. Don't ask me why they call it reflexive. Sort of pointing back at itself, I guess. Symmetric. So this one is if. So again, if you think of in terms of tuple, if this guy's in here, then this guy is too. So that's more like you're going to have A, B, you're also going to have BA as an element of your relation. And transitive is a little bit harder to draw for this guy, but it's basically, it's easier when we look at the pictures. So if we go back to the digraphs, which we will in a second, then if these two, if X is related to Y and Y is related to Z, then X is related to Z. So you sort of got this triangle, you go around. So these three properties are really special. If you have them, you can say, get this quite nice result we're going to talk about very briefly. So as a picture, you've got this guy over here, A points to itself. We draw the graph. Symmetric, A points to B, B also points to A. Anti-symmetric, don't worry so much, but the opposite, so it doesn't. And transitive, I think this one, the arrows are broken. I think you got a, there's a the picture's got a problem. I think the arrow should be this way with the way they're talking about it. So it's going that way and that way. So A is related to B, B is related to C, and then C is related to A. Maybe the way they've written it here is different. No, I think the arrows are just funny. They're all flipped. So if A is related to B, AB is an element of the thing, and then BC, then also AC is an element of the relation. Cool, I hope that's somewhat clear. It's basically about these tuples, whether they're in the set or not. And for all, in particular, remember we saw this symbol? When you're going through these, look at this, it's got for all. So I hope last time, from the last lecture, you got this rough idea that if you ever see a for all, how you would disprove it would be to show that there's any example where it's not true. So if you ever get a question like this, you're going, is this set reflexive? And you can go, well, no, because C is not pointing to itself. That CC is not an element of the tuple. Or if it's, is it symmetric? Well, AB's in there, but BA is not in there. So, okay, cool. So maybe 86, you can sort of see those directly straight away. So we've got some reflexive terms, but 2, 2, 4, 4, but we don't have 3, 3. So it's not reflexive as a hint. So 3, 3's got to be in there because it was for all. Again, I'd draw these pictures. So I probably really briefly. So when we were saying about just the way you draw these graphs is you draw something like A, B, C, and you draw all these squiggly lines in there. So for certain relations, you'd have this guy points to A points to himself, A points to B, and then you can hopefully say whether this is, you know, if you want it to be reflexive, C has to point to himself, B has to point to himself. Doesn't have all the other properties, but roughly, that's what's going on. I'll just undo that. Page 3. Anyway, go back to the notes because we've got a lot to cover. We're just getting through relations. So special sort of relation, identity relations, boring relation. It's where it's only in there if x equals y. That's boring, but it also, you should be able to show whether it has these properties or not. So it definitely has reflexive. Challenge for you guys to see if it has every one, and it does, is the answer. But see if you can understand that for yourself. So again, this is just a repeat of what I said before. You're going to try and show, like we talked about in the proof things, if anything ever says for all, you just have to find one example where it's not and you've disproved it. That's what this stuff's going on about. Skip examples. More examples, go through them yourselves. It's quite natural thing. It's just have to go through is make sure you understand what all these terms mean. What we're really building up to is a special thing. I'll just make sure where I'm up to. I feel like I'm in a reasonable spot. Okay. So, I'll just make a note. 93 is a good one to try for yourself, I think, to make sure you understand it. So we were talking about proof methods. Is there another one like that? There might be, yeah. Reflexive, sorry, 90, that does this too. So proof methods, these ones are really good ones for practicing proofs from the last section. Basically, you just write down the definition of the inverse relation. We talked about that before. So it's somewhere back up here. Remember, you just flip whatever's in the tuple. Sorry, yeah, here we go. So you basically just write this guy down, write down what transitive and reflexive mean, and see if you can work out what these guys are. They're quite, the proof is basically just writing down the two definitions and you can see straight away. Yeah, If it's reflexive, is the inverse mapping also reflexive? You just write down what does it mean for it to be reflexive? What does it mean for the inverse mapping? You should just see it straight away. Sorry, sideshow, but if you want to practice proofs, they're really easy ones. Okay, equivalence relations. So this is what we're building up to. Talking about these concepts, like, yeah, cool, that's a property of a relation. Why do I care about it? This is sort of deep, and it's the sort of thing mathematicians think about. So remember we were talking about a partition when we were doing the set stuff, which was like a month ago, which is sort of crazy. So it's a collection of non-empty, mutually disjoint subsets. So, you know, they don't intersect. The intersection's null set, and the union makes the whole set. So this is an example. So these are very, very thin lines, nothing lying on those lines. X is partitioned into A, B, C, D, E, F. Now, okay, let's see if I can explain this well. Now, given a partition on set, the binary relation R induced by the partition is defined as follows. Okay, for all x, y log of A, blah, 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 if and only if there is a subset AI of the partition containing both x and y. Now, what we're going to go for, so parts of maths you would have definitely heard of a theorem before. This is going to come up. And we've got a few lemmas down here. I don't know if anyone's heard of a lemma. A lemma you can think of as a small theorem. It's a bit of a value judgment on the importance of a result. But if you think of it as mathematicians, it's like, this is a small result. It's not crucial to, it's crucial to my argument, but it's not important. I'll call it a lemma. So another theorem, but theorems are big things. Lemmas are little things. You use lemmas to build up to theorems. So it's sort of like if you're writing mathematics, you want to bring attention to the theorems or the big things. Lemmas are little things you just want for results. There's lots of examples in maths where the mathematician got it wrong. The lemma's more interesting than the theorem they were trying to prove. Blah. Okay. So if we've got a partition of the set and a binary relation R induced by the partition, which we were just saying what that means above here, then it follows that R is reflexive, symmetric, and transitive. Cool. So, okay. Try and work out what I should say about that. Okay, so, okay, so the property of this relation induced by the partition is has these properties that it's reflexive, symmetric, and transitive. This is important in machine learning. A big part of machine learning is classification. Classification, you can show here's, like, say it's image processing. So go, here's a bunch of pictures. All of these pictures contain a picture of a cat. All of these pictures contain a picture of a dog. All of these ones contain a picture of a monkey, and maybe something else as well. So we can think of each of those as a partition of the set of photos. And you can go that this relation induced by the partition has the property that's reflexive. So, you know, this one is, this cat photo is a cat. It's symmetric and it's transitive. Okay, what we're trying to build up to, there's also this thing called an equivalence class. So you name this on, let A be the set and R be an equivalence relation on A. For each A in A, an equivalence class containing A, it's got this, so that's for a particular element of the set, and you denote it with these square brackets. The set of all X in A, such that X is related to A in R. So in my example, that's a particular photo of a cat is equivalent, there's an equivalence relation that it's got this relation induced by the partition. So every photo of a cat is equivalent to this photo of a cat. I feel like I'm explaining this badly, but we'll go on. So what we're trying to build up to, I'm just going to skip through fairly quickly. Got this theorem. Okay, so this is really going the other way. So let's make sure we got this guy, yeah. sorry, theorem 11 is basically saying the other way. So what we've got here, the equivalence classes of R form a partition of A. So I might have skipped the lemmas. Yeah, no, that's sort of useless. It's just saying the equivalence class of A is equivalence class of B if they're in a relation and their intersection is empty. So that's how you build up this form of partition. The equivalence classes form a partition of A. So it's really this two-way thing that you're going, so we got here, so a partition, the binary relation induced by the partition is reflexive, symmetric, and transitive. And if you have these properties of a relation, it induces a partition. So it's an if and only if thing. It goes both ways. So I'm going to, it's sort of hard to come up with a practical example of why you'd care about this. It's a little bit abstract. Struggling to think of an example. Relations in general, I'll just say briefly, why you care about relations. And for data scientists, big thing will be using, a lot of you, I guess, will go off and have a career and you'll be using SQL. Has anyone used SQL already? Has anyone had experience with databases? Yeah, so SQL is a relational database. So it was about 1970, this guy at IBM, when all the operations you're doing on data in a relational database are, you can write as relational algebra. It's an algebra of relations. So some of these things where you're going, join, natural join, inner join, outer join, are all all set operations on relations. So when this comes in, you can think about that. If you learn a bit about SQL, you'll see about relational algebra is a big thing. It's the basis of those sorts of query languages for relational databases. Lots of different sorts of databases, but that's the main one. If you're off in a big company, you'll be dealing with SQL a lot. Okay, so relations. That took longer than I expected, but we've got a race. So functions, this is where it's getting really interesting. Functions are more important than, pretty much, particularly because of calculus. The idea of a function is super important. You sort of get so used to it that you don't even think of relations. It sort of goes off into the background. Becomes important every now and again, but functions, sort of everything. And we said really briefly what the definition of a function is, because it's so important, we're going to do it again. So we're going to talk about univariate functions to start with. That's functions of one variable. There's lots of names, and the names can be a little bit confusing. Everywhere, everything's a function. Everything in machine learning is a function. You're trying to learn functions typically is what you're doing. We'll talk a bit about that in the application example. So again, we've got a binary, what the definition is, we've got a binary relation. So going down to here, lots of definitions. The binary relation from set, whatever this guy is, funny x to funny y, is said to be a function. You also hear it called a map or a mapping if it satisfies the following. So again, for all x in the first set, so every little point in the first set has to be able to have a unique value in y. So this is the really important one. It's unique. Uniqueness and for all, then it's a function. So if we were drawing, going back to this dodgy picture, we'll see that this relation I drew here is not a function because this guy does not map. So remember it was for all. So 6 does not have a corresponding one over here. And this one over here, 1, he goes to 2 values. So he's not unique. So what would be more like a function is, again, we're going to A, and you've got 1, 2, 1, 3, 5. Over here, we've got the set B, A, B, C, D. Just try and space it out so I can see it. So every one of these guys has to have an element. So we can have, so this would be an example of a function. 1 going to A, 3 going to C, 5 can go to C too. That's okay. That's still a function. What's important is everyone in A has to go across to something in B. And you can't have one thing in A splitting off into two things in B. It can only go to one thing on the other side. Again, we're going to consider, that's later on, the onto thing. Onto is a special relationship, yeah. So many different ways you can have this. You can have, skipping ahead to the lecture land, and you've got one-to-one, onto, or you want to call them injective or surjective. And the other one is a bijection. We'll go through that in a little bit later, but that's good. Okay, so they're particular set types of functions. But all you need in general for a function is you got to go, every one of x is unique y. First one you can skip around a little bit. I'll maybe talk about that in a sec. The multi-valued thing is a killer. You can't have that, but you can. There's ways of dealing with it in applications anyway. If you want all the nice properties of functions. And the biggest one is what your guys are leading up to is calculus. You can do calculus. Calculus is such a powerful tool that if you can use it, you're going to win. So for example, so here we go. This guy, square root x is not a function from R to R because it's not defined, it's imaginary if you're less than 0. So it's not from the reals to the reals, but you can salvage it by just going, it's not from all the reals, it's from the positive reals to the reals. Yeah, but notice, you know, so we're going to talk about where you're coming from and where you're going to. They've got special names. And also the little bit you're actually going to on the other side. So again, definitions. So again, I'll let you do the examples yourselves. So we've got these special words. Set x, so remember this is the set. So go back to that picture. That's that big blob in the bar pie type thing. That's the domain. Set y is called the codomain. And this one's probably more important. The codomain is sort of funny because it's like you can reshuffle it, but you know, you're sort of free to say whatever that is. But like if you've got a function from the reals to the reals, the main is the reals, codomain is the reals. You're not going to go to every element. You know, you're not restricted to go to explore the whole thing. So I'll go back to this guy. So what we got here, this is, I'm going to type, not try and write, because that will be a freaking disaster. Domain, codomain, and the image is the set of all the ones it actually goes to, which is A and B. So you notice not everyone's getting mapped over to, just goes to A, just goes to C. So that was the image, and it's called a couple of different things. And you'll see all these mixed around. So for a single one, that's the image, and all of them together is the range, and sometimes called the image of x under f. So it's really confusing notation, really old words. Hopefully that's clear. So domain, set you're mapping from, codomain, set you're mapping to, the range is the set your actual values you actually hit. More important, that one needs to be, I'd say, more important than the codomain. Okay, again, we're going back to these arrow diagrams and representing things as bipartite graphs, because you know it's just relations again. That's fine. Okay, so again, an arrow diagram again. This guy's coming up again. So we've got pictures. Hopefully you can see a little clearer than mine. This guy's a function. Everyone in A getting mapped across to something. There's some missing. So really quickly in the chat, who wants to say what the set that, oh, there's questions underneath. Domain, codomain, and range. Does anyone want to write that down? See if we're clear on what these things mean. as set notation. So what do I put in here? Yay, good, someone did it. A, B, C, D. Codomain. Apply. Codomain is everything in the other one. So 1, 2, 3, 4, 5. The important one is the range, is the values you're actually hitting. Yeah, 2, 3, 5. Magic. Cool. As I say, range is the important one. It's sort of free to redefine what your set is anyway. So, and again, we've got the relation, A maps to 3, so f of A equals 3, f of B equals 2, nice visual representation, f of C equals 3, f of D equals 5. So all this stuff about arrow diagrams hold. It's a directed bar pie chart graph because it's a relation, because functions are a subset of relations. Yep, that's fine. More examples, go through them yourselves, I'd say. Now this one, again, what we're building up to is, I'm going to give away the plot, building up to inverse functions. So inverse function is really, if you have an inverse function, it's really useful. You don't call it, because not everything's invertible. Maybe your intuition will say why something won't be invertible under the flip, and what properties of the set means it is actually invertible, which is the stuff we were going on about before, if it's onto one-to-one or a bijection. Going to go over that again, but if you're not worried about, we had the inverse relation. The inverse image is, again, you just flip the values. So the inverse image of y equals the set of x such that f of x equals y, which is the same in that relationship of just flipping the tuple. Just change the direction of the arrows. That won't necessarily be a function. It will be a relation, but not necessarily a function. And try and build up to the ones that actually are functions. So if you have an inverse function, it's nice. Okay, where are we up to? So that guy. Inverse image is important. Okay, so skipping over lots of examples. Just this one is a notational thing. You'll often hear a sequence is a function from the integers. Find the set of integers greater than or equal to some fixed integer, write the sequence, blah, blah, blah. I think the next chapter is all about that stuff, which you'll do with Hamid, so I won't say too much about it, but just as a prelude to what's coming. And again, okay, this one's important. We've got, this notes are a little bit tricky in that they hide important stuff. Oh yeah, I missed that one too. So this one's important. So like we had before, identity relation. There's an identity function which just returns the value you put in. That's good. Nice to know. That is a fun thing that exists. Useful, but it's more useful when you think about inverse functions. The next bit that's important is, just for notation, is this guy. A binary operation on a set is a special kind of function from the set that's the product space of this to another set y, where usually y is a subset of x. Funnily enough, I didn't know this was coming up when I was doing the example for last week. In that example I sent you of the 200 terabyte maths proof, that was all about coloring Pythagorean triples. That's an example of one of these guys where you've got this, it's a binary operation, but much more sensible one is you can think of it as addition as one of these binary operations, where you take two numbers and you get another number out. So because it's an element of the product space, that's why you have the tuple as the input for this guy. So you're taking 3 and 2. Funny thing is, we're saying it's a tuple, but for addition, it's symmetric. So you can flip 2 and 3, you get the same answer. when he's saying make sure you understand the parentheses, remember that's the operation is plus, passing in 3 and 2, and you'll get 5 out. So example here, find an element of Z with an image of 1. So image, remember, is when you pass it through the function, what do you get? There's an infinite number of solutions here. You could say, 500 plus minus 501 or something will give you minus 1. So the input with that would be a tuple where you'd have 500 minus 501. Okay, binary operations. Okay, we've got a little bit of a non sequitur example here about coding theory. I don't know if that's interesting. I can talk to you about super interesting stuff. Just examples of functions. So 63. I think we're getting into examples of functions. Okay, so where are we up to? So we've gone through what a function is. We'll quickly say a little bit about examples of functions that you'll see or not see, depending. You'll see Hamming distance comes up in coding theory. I think this guy's more interesting at the moment, exponential function. We're all sort of living through an example of an exponential function at the moment with coronavirus. They're slightly terrifying things at times. So this is an example of a real function. By a real function, we mean it's mapping from the reals to the reals. Again, this is the domain, codomain. It's not actually mapping to all of them. It's just not, the image under the function is just the positive reals. Assume, I don't know everyone's background, but I assume you've seen an exponential function before. That familiar thing for everybody? Yeah, okay, too easy. I won't say too much about it. So I think we're going to so we'll do some examples of functions, and then we'll stop for a break for a little bit. You can have slightly more exotic functions like this guy, Hamming distance function. So when you transmit messages, it's important to use coding theory. Anyone ever heard of error correcting codes and Hamming distance function? Is this a new thing to anybody? I assume it is, maybe. Depends if you've done digital electronics before. It's like the basis of sending information on a noisy channel. You can think of, everything on a digital computer, you represent it as ones and zeros. So you encode it somehow. So like binary encoding, you might just go zeros to a certain bit size, 0, 0, 0. Then you transmit this message, and the whole idea of coding theory is how can you send at the lowest level that there was a problem when I transmitted the message. And you can say a really simple way of doing that is just summing up the bits and having a parity bit on the end, they call it, where you go, well, if you sum to, is the remainder 1 or 0, and you make it always 0 by adding a parity bit. This Hamming distance function is to do with the theory of that. Then you can have, so that's an error detecting code, a really simple one. There's much more complicated versions. Then you can have error correcting codes, which is even better. So you pad your message with special little bits of message, and you can get rid of errors, detect errors and correct some of them if the noise isn't too high. Hamming distance function is a thing that comes up in this theory of coding theory, and it's to do with the amount of substitutions you have to do to a bit. So how many bits do you have to flip from a 1 to a 0? The minimum number to turn one set of zeros and ones into another set of zeros and ones. So that's a pretty exotic function. And these distance functions come up all the time. You've been doing linear algebra right at the start. You talked about norms. A norm is an abstract notion of distance. Really important. Trigonometric functions. We'll get through this. So these are, I probably don't, there's so much you can say about this, and I probably won't have any time to talk about it deeply. But when we talked about complex numbers, you can represent complex numbers as sines and causes forever ago. In terms of, You know, if we do the Argand diagram where you've got real and imaginary numbers, there's an angle and an amplitude. Yeah, so basic ones, cos, sine, tan. You should have done all this stuff in high school to death. Comes up if you're doing or repeated phenomena, anything periodic. If you're doing traditional signal processing, which is actually my background, did a lot of signal processing and control theory before I got into machine learning. Sort of like one of the forefathers of machine learning. Any repeated signal, periodic signals like transmitted, you're going to have sines and coses everywhere. Tans, and so I won't say too much about this. It's pretty dull. You should be all familiar with this, so we'll skip over. But we'll say a little bit more when we talk about multivariate functions of sines and coses. But trigonometric functions, really, you've got an amplitude and a frequency, or a period is the way to think about these guys. So you can alter the amplitude or you can alter the frequency by changing this number underneath. We'll take a little break. Rocketing through all this stuff. I'm sorry if it's a little bit quick, but take a 5-minute break and then I'll get back. Okay? Okay, guys, little break. Is everyone refreshed somewhat? It's very late. Very difficult time to do a lecture, but I hope you're all going well. It's soldiering through. Okay, so hopefully I'm sharing my screen. Okay, so we're up to 4.5. So we've had a really, really big race through relations. Relations are a subset of the products, of the Cartesian product of sets. Functions are a subset of relations, and functions have all these useful properties. And some of the things we're trying to build up to, what I'm trying to build up to here, get and introduce enough concepts here so that when you hit the multivariate calculus you're going to do later on, that you can see some of these useful things. This one's super useful, and I hope you can see. And when I talk about the example application at the end of this lecture, I'm going to talk a bit about neural networks. So you've never, everyone's heard of neural networks, I'm sure. I'm going to say what one is, show you an example of a really simple one, an example of a really complicated one, and how they work. They're really based around like a huge part of this composition of functions. And when you have this composition of functions, also you want to know how errors flow through these functions. Like if I change a thing, what does it do at the output? So I want to try and make the output good. So how do I propagate errors through this chain of functions? This is all composition of functions. So this is really important. It's really simple though. So basically all you're doing is you can compose functions, and the composition of functions has properties, important ones. Certain things, you can say certain things about certain types of functions. So you've got two functions. I don't know why I'm saying Z in these notes, but we've got F and G. Oh, this is a particular example. What we can do is we can define a function. So in this example, he's saying we've got, in the notes, we've got f of x equals x plus 1, x squared. What we can do, I'll just do this, I'll write this out, it's important. So we've got f of x equals x plus 1. Well, uppercase there. G of x equals x squared. We can define this operation, G, I'm going to do, sorry, I don't have the right symbol, Unicode symbol here, so I'll just try to know. So where we pass f of x into g of x, g of f of x. So in this example, it's really simple. You just put f of x inside g of x, and we get, so it's h, I think they called it, h of x. So this little circle is the notation for composition of functions, where we're going to put g inside of f of x. Again, this is all about, when we talk about neural networks, it's all about composition of functions. You take a thing, usually a linear algebra thing, you pass it through a nonlinear function, you do a thing, you do an aggregation, you do it again and again and again. Big chain of operations of compositions of functions. So in this example, h of x, all we're going to do is we're putting h of x equals, we're going to put x plus 1 inside squared. So we've put f of x inside g of x, and we're applying g of x to the output of f of x. So we can define these chains of operations, composition of functions. So we got the right answer there. An example of composition of functions, composition of f and g. In this section, we shall investigate this concept. Yeah, I probably got the order wrong. G of f of x. I hope I said that the right way around in my notes. Brain's fading. Yeah, I got it the right way around. That's cool. Sorry, I had to check so I wasn't leading you astray. So we've got this composition of functions. So it's red circle f. this composition is really important, particularly when you get to calculus, because there's results about how you can apply a derivative, if you're familiar with a derivative. I'll probably say something that's really leading towards what a derivative is if you're not familiar. How you pass derivatives through functions, and that's how you can get sensitivities of things to other things when you've got this big chain of operations, which is basically how neural networks work, the training of neural networks. We're not going to talk about training neural networks today for the application, we're just going to talk about what they are. Training's fairly subtle. By the end of this course, though, you should have a really good idea of all the machinery you need to be able to do that, though. So that's the composition of F and G because an element X. So again, domain is where you come from. So that's this set funny X. I'm drawing that with I should use my pen. I'm using my mouse, which was really dumb. Codomain of the composition is this guy. So you've gone out to Z. So the range, though, is again, I think that's codomain I just drew. The range is the image under G of the range of F. I don't think that's quite right, but that's this little set here. So that's that little gray shaded thing. So that's the range. So you just got this chain of operations. It's really simple, really, really powerful. Really powerful when you've got calculus involved. Yeah, which you'll get to very shortly. Some examples. Again, these arrow diagrams, you can do it to your head explodes, but you can sort of just trace things through. So you're going like A goes to 1, 1 goes to Y. Some of these guys are not part of F, so they're not part of the image of F, so you're not going to get them through as the image of the composition of the functions. Basically trace the arrows through. So for this one, just to be clear, this guy is the domain, Z is the codomain. The only ones that actually have values, if we trace them through, A goes to 1, 1 goes down to Y, try it with my pen, B goes to 3, 3 goes to Z, this guy goes to 1. So the only ones in the image under the composition of functions are Z and Y. Do the rest yourself, that's pretty straightforward. See if I didn't miss anything. That's the idea of a composition of functions. Pretty straightforward. Really powerful though. Really, really powerful. Okay, so if this one's sort of some little things buried in here. Theorem 12. If you do, why is the identity function special? You could think of it, again, thinking like a mathematician, you sort of try and see all these structures across different things. Identity matrix, you multiply it by a matrix, same thing back. Could do a composition with an identity function, you get the same thing back. And it doesn't matter which way you do it. I hope you can see whether it matters, whether the order of the composition of function matters. So I'll leave that for you to think through, but this identity function, which we talked about a little bit before, like the identity relation, that has this special property that if you do the composition of F with the identity, you get the same thing back. You do the composition of the identity with F, you get F back. And here's a special one, which is what we're building up to, that there's one-to-one correspondence. This word, you won't have seen this. We've got one-to-one functions. We're introducing some stuff we haven't talked about. We're going to talk about this in a second, but if this F is a one-to-one correspondence with inverse function, so it's got an inverse function, then if you do the composition of the inverse with itself, you get the identity function, or itself with the inverse function, you get the identity function. This is like matrices. Matrices are a function. The operation of matrix multiplication is like a function. You can go, or is a function. You can go take a vector, multiply it by a matrix. You get a matrix, you get a vector out. Maybe there's an identity operation too. But this more generic version of this is with functions that this is the magic thing. If there's a one-to-one correspondence with inverse function, then this result will be true. Which is what we're building up to. So you've got this one where if the two functions are one-to-one functions. We're going to say precisely what that means in a second. Then the composition is one-to-one also. Really useful results. Cool. So this is where we're getting onto. So one of you guys said onto Landon in the chat before. So try and get this bit super clear because this is a very important concept. Really, this is the one we're building up to, because if you've got an inverse function, it's great. Came up for me professionally recently, doing something with sampling, but probably a bit detailed to talk about. Okay, two important properties of functions may or may not satisfy. So this is really important. Remember that first one we drew, or I drew, sorry, might not have satisfied it. You know, again, relations, not all relations are functions, not all functions are one-to-one, not all functions are onto, not all functions are one-to-one and onto. But if you've got that, then you've got a magic thing called an inverse function. Yeah, so that's this guy. So if you've got both of these guys, then you can invert it. And if we said about, you know, when I said about the inverse image where you flip the arrows around, you know, and what makes something a function in the other direction is that it doesn't map to two different things. So if two things map to one thing, if you try and flip the arrows, it won't map to the other way. So, okay. So let f be a function from set x to set y. The function f is one-to-one or injective if and only if, so we talked about that last time, what that means, for all elements x1, x2 in blah, if x1 equals f of x2, then x1 equals x2. Okay, so that's the definition of, so you get these names, I'm sort of, one-to-one's a good English one, you've got these funny words, but these came up in set theory when we were talking about cardinality. Very briefly, maybe we talked about injective, bijective on a set for relationships between sets. When we were talking about cardinality, whether you work out whether something's bigger than the other thing, very briefly, we touched on it. So if x1 does not equal x2, then x1 does not equal x2. So again, definition of a function was everything in one set had to map to something in the other set. So this guy is an example of not one-to-one because 5 and 3 are both going over to C. So if I want to make this one-to-one, everything in this guy, really quite tricky, has to map to a unique element on the other side. So not everything in, for one-to-one, not everything has to have a value on the other side, one-to-one, but every guy in here maps to something and everything it maps to is unique. You only get the same thing if the same thing's put in. Again, there's a finite set we're talking about, same thing carries over to infinite sets, which is more what you're interested in with numbers. We're usually talking about real valued functions. So we can immediately see if we do the inverse image of this guy, if we flip the arrows around, it's not going to be a function because this guy is not mapping. Remember, everything in the domain has to map to something. And if we're flipping, doing the inverse image, domain becomes the codomain, codomain becomes the domain. B is lonely, he doesn't get anything, doesn't get anyone. So next concept is we're going to go, again, just really quickly note, sorry. Again, if you got a proof and it says for all, show it or show it's not. To prove it's one-to-one, you have to show it by direct proof. Show it's not, you just have to find anything. Again, we'll kill it. Okay, there's a little section on a hash function. These are super useful in computers. It's almost one-to-one function. A little bit of a sideways thing. I won't say too much about that. There's actually lots of different kinds of hash functions though. You've got cryptographic hash functions versus, you can think of these things called locality sensitive hashes. I won't talk too much about that. I might come back to it if anyone's interested, but we won't say because we're running out of time, as always with me. Say this one. So the next one is onto. This is really important. So f be a function from set x to set y. The function is onto or surjective. Injective, one-to-one. Onto is surjective. If and only if any element in y is an element of y, it's possible to find an element, x element of x, with the property that x equals f of y. Blah, 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 very mathsy speak. Yeah, it's onto, again, this is what I was talking about with it being lonely. If you've got, I'll go back to this picture, sorry. So this guy is not onto because B is lonely. It's probably hard to do it with this many set elements. Let's just delete one. Oh no, I can't delete the text. No, I'll draw a new picture really quickly. So we got A, 1, 3, 5, B, A, B. We can have a function as long as it doesn't go. Remember, it only has to go, we can go this. So what this is saying about onto is everything in B, you can always find an X for everything in B. Which is what I was saying before about, you know, if you want to flip, you know, if you want to find the inverse relation, domain, I'm going to say it again so you remember it. Codomain. We're going to flip these arrow directions. It's only going to be a function if it goes, you know, everything in B when you flip it around. Sorry, my son's annoying me through the window. If everything in A, everything in B is mapping over to something in A. The problem is this won't be a function. No, not necessarily, right? Sorry, I only just missed you. Actually, sorry, I lie. Yes. Yes. Sorry, good point. Yeah, so when you flip it around, this guy won't be a function because A is mapping to 1 and 3. So the one we want, if we want it to be a function in the other direction, is we want both of these properties. And that's, let's see where he is, a one-to-one correspondence. So this is a little bit confusing because it's too close to one-to-one. It's always got this correspondence afterwards. So bijection is better for this one, where it's one-to-one and onto. So it's injective and surjective. And this lets you, if you flip all the arrows around, you do the inverse image, it's a function as well, which is really important. And then that's how you get this magic property where if you compose them, you get the identity. Ta-da, it's called the inverse function. Hope that's clear. Really useful if it happens. Again, in terms of a plot, you know, I try and make sure I get the right one. So we've got an example of a function that is a bijection, which is x cubed. Hopefully you can see this for the reals. It's this guy. Sorry, this guy. My kids are distracting me. It's really annoying. Yeah, this is x cubed, and you can sort of imagine flipping it around this guy, and that will be the inverse function of this, which is this x to the 1/3. Again, one-to-one and onto, hopefully you can see it in terms of real valued functions. I'll just say practically, if you have a function that isn't a bijection, you can often chop it up, which is what I was saying, you know, like the codomain's not always as interesting as the range because you're sort of free to rejig what the codomain is, and you can chop it into pieces and they might be invertible on those ranges, which is a way of dealing with this in real life. So like say you get a function that's flat, like particular example, if it went up and down, you might be able to chop it between here and here, and it's invertible in pieces. It's hard to work out where the breakpoints are often, but it's a thing you can do. Here's an example of the inverse function of The exponential function is a logarithm, which is a really useful function. Hopefully you can see if you sort of flip it around like we were saying before, you get the inverse function. So you do this composition. If you take the exp of a log, you get 1 out. It's an identity function. Oh, sorry. Yep. Okay, and same for trigonometric functions. There's an inverse of trigonometric functions. I don't know, maybe that was in your assignment, but inverse trigonometric functions are often used in machine learning for neural networks. So I'll talk about that when I get to the example. They have this useful shape that when you're trying to talk about stuff. So this guy. So really going to quickly talk about real functions of several variables. Sorry, one sec. Okay, real functions of several variables. We were talking about univariate functions. Again, you know, you have a tuple product space. You can make the product space bigger, A cross A cross A cross A. The Cartesian product bigger. And you can have multivariate functions. Okay, talking a bit about calculus. So this is where you're going to get to, hopefully. So some really simple examples of multivariate functions. You'd be familiar with these from examples. The volume of a cylinder. We've seen that in high school. You can think of this as a function of the radius and the length. It's a 2-valued function that gives you a volume. I think there's a plot down here. That's the volume of the cylinder. So this plot, I'm not sure what the axes are because they aren't labeled. I would guess that this one's blowing up like a squared function. We go out this way and this one's linear. It looks like a straight line up here. So if you took if you wanted to work out the volume at a particular length, you take a cross section through here and look at the R, how it changes with R, same the other way. Take a cross section of this. Yeah, it's a natural extension. You go from univariate functions to multivariate functions. All of these concepts come across. It's really hard. You know, some things get a little bit harder when you go to multivariate functions. Yeah. Okay, so we've got an example of the vibration of a string. This is written in terms of x of t. So think of a guitar string, and you watch it in time, but it's a standing wave. So harmonic, you're doing this. I don't know if you see me doing dancing for you in the window, but it's got this particular shape where there's an amplitude, you have frequency in space, and you have a frequency in time. And this is the sort of plot you get. So again, if you take a cross section through or across, you'll get different things. So in time, it'll be wiggle, wiggle, wiggle. And it's sort of the same, but with fixed constraints on the other side. So you might get something like that. Depending on where you did it in time, it'll get smaller and bigger the other way. So that's like a spatial cross section with each of these being different times. This is a time cross section through a space. Pretty natural. Visualization of high dimensional functions is actually really important when you're doing machine learning. Talk a little bit here about planes. This is, I won't say too much, but it's like generalize a line. You can do a line in 3 dimensions, but you can also do a plane. So flat surface, there's lots of ways of parameterizing a plane. That's one of these things you gets a little confusing. There's many ways you can parameterize this. This is a useful way. Going back to your vector calculus, another way you can parameterize a plane is you can specify, so try and draw it on here. So this is saying about the slopes in different directions. When they're parameterizing the plane this way, A, B, C equals D. You can also do it by a point and a vector that's normal to the surface is another way to parameterize a plane. Sometimes that's really useful. I've done that many times. I guess why we're talking about planes is these things called contour diagrams. In 2D, you can take contours by intersecting a plane, usually at a fixed Z level. through a surface, and you'll get these funny shapes that let you visualize a 3D shape in 2 dimensions. So you get to reduce the dimensionality by 1. Be really useful. Contour diagrams, using Mathematica or something. It's really dead simple to do contour plots. We're talking about radial symmetry here. So if you've got anything of this sort of form, you can get circles. So there's lots of examples of circles, but the difference is the spacing between these guys when you take contours. And a saddle is another shape you can get where it's curving one way in one direction, one way in the other direction. Don't know how much to say about that. That might be useful for question 5. People were asking, thinking about these shapes. It's also a plane, plane generalization, so it will hit everything if it's got a slope. Giving you a hint. I don't know how much to say about that. It's pretty straightforward. You'll talk about in calculus, when you're doing the calculus in your next sections, probably section 6 or something, not with me, this is my last one. You'll be interested in finding like lines that approximate a curve and planes that approximate a surface. The techniques for that are calculus. And so there's some hints here about how you might do that, about taking a step in the direction of the surface. And that's pretty much where you get to calculus. Yeah, planes. I won't try and draw for you here. But I would not with a bang but a whimper. So we got through this huge section of functions. I've raced through it really quickly. Again, what I would worry about for you guys is, so I tried to highlight the definitions. A lot of this stuff's just definitional. Looks like you guys have got it. Again, function, I'll say it again, again. Relations are a subset of the Cartesian product. Functions are a subset of relationships where everything in one side is mapped to something on the other side, and one thing doesn't map to 2 things. Then if we want an invertible function, think about how you make it go both ways. And that generalizes to everything, and you should be able to cover most of the things you're going to come across. That's probably enough. I'd go through the examples yourself. They're all sort of simple for this one, which is good. I think I saw any that I thought were really nasty, but feel free to ask for help when you're going through. Anyone, any questions before I start on an example of a function, a really important one that you guys will probably learn a lot about, not knowing more than me about. I've spent a lot of my professional career dealing with these guys. Any questions before I go on? No? I'll take that silence as. Okay, well, in general, it's a quadratic surface. So if you want the hint. You only might have said about quadratic forms. Is that something you can say? Have you heard of that before, guys? Did that come up? When you were doing matrix stuff, you might have seen that, where you might have something like X. Yeah, and in general, what you're talking about is a quadratic surface. Quadrics, they're called sometimes, and there's lots of results about if you intersect a quadric with a plane. Sometimes you get an ellipse, sometimes you get a hyperbola. Yeah, that's the magic words you'll be looking for, probably for question 5. That you guys are asking at the start. Okay, cool. Yeah, probably a big hint there, but oh, I jumped too far ahead. Okay, we'll talk about neural networks now, which are really fun and really quite surprising in my career. Like, I'm not that old, I'm fairly old, but I'm not that old. But when I was a graduate student, I would say, check the time, it's like The last time I talked about AI winter, and one of these things that came up back then, it's like 1970s, even early 1960s, people were talking about neural networks. And the idea was semi-biologically inspired. Sort of went way, way crazy away from that. Not even close to biologically inspired now. I'll say a bit about a neuron because I can. In your brain, if you're lucky, you have these little cells called neurons, and they're funny. I probably should just get a picture. They sort of look like this, and then they go and touch other ones. This can be long. So they've got these connections. This is people looking under microscopes. It looks like probably, I don't know, I won't go on the internet to look for pictures, but so this is a really bad picture of a neuron. So people were trying to work out how these guys work, and it looks like all these connections, these dendrites up here, these bits, nope, I won't do that. The dendrites were connecting to other neurons. So there's this high degree of connectivity between neurons. And what happens is, one thing you notice is that at a certain point, the neuron gets stimulated and it will send a wave of electric field down the neuron, down to here. And these guys will be touching the dendrites of another neuron. So it'll be here, we're touching these guys. He goes off, has his own thing. It's a little bit mysterious. And this, what it looks like, the behavior, this is where neural networks are coming from, is that you've got a bunch of inputs over this side. And this is like a bunch of outputs. And at a certain point, the neuron decides that it's a good idea to send the signal from the inputs to the outputs. And the really dumb model of this is, so this is the biological inspiration. It's really way more complicated than that in real life. Lots of things can happen. People aren't even sure about big parts of it. This thing about this electric wave traveling down the neuron was the Nobel Prize for Hodgkin and Huxley, working out with a really finicky experiment where they actually stuck a needle up the inside of an axon, this thing called an axon, and they stuck a little electric probe on the outside, and they measured all these concentrations of chemicals and worked out when this would send a thing down. But the big thing is, what you have is that this guy acts like a sum. You sum up all the inputs, all these inputs here as a current, and if you plotted that, what happens is, it's like you're summing up the inputs, summing up the inputs, summing up the inputs, and then when they reach a certain threshold, spike happens. And then this spike travels down the thing. And if you don't reach this threshold, this guy decays back down to 0. So there's this non-linear operation. So we talked about linear function. I probably should have. You've done linear algebra. You should know what a linear function is. General is a non-linear function. That there's this non-linear activation function that once you've summed up enough of these inputs, across this threshold, the spike happens, and then you get an output. So it's a little bit, we were talking about logic. It's a little bit like a logical circuit. So a lot of people, like famous mathematician John von Neumann, who designed computer architecture, he was sort of big on that. It's like a digital, it's like almost like digital circuits, but not quite. There's a lot of randomness in there. Not sure. So people went, well, the research branched into two paths very early on. You've got people who are biologists and electrophysiologists, and they're going, well, I want to actually understand what's going on in people's heads or animals' brains mechanistically. And then you've got computer scientists who go, well, this looks like a really interesting version of computation compared to logic. Last time we were talking about logic programming and the problems you can have with that. Maybe there's something in this. And at a very, very base level, you know, here's a simple version of a neuron, I can just use linear algebra and some sort of activation function, and then I can get an output. I'm going to show you and see how this goes for, just undo my picture. We're going to go for an artificial neural network. So if you see that, people don't tend to say it, they can say deep neural networks and stuff. Artificial neural network in EU. So you'll hear about deep neural networks and stuff, people like that. But artificial neural networks, the big split. You've got biological neural networks where you're trying to simulate reality. Artificial neural networks where you're going, whoa, this is interesting. It's not quite logic. It's something sort of smoothed out like logic. Where can we go with this? So, like I said, activation function. So sort of behavior you want is this sort of, it's almost like a logic gate. So if I have an input, strength of my input, I want it to go between 0 and 1. And I want some sort of, instead of a logic gate, if you're thinking like we were talking about last lecture where we're going, it's true or it's false, you can think of a logic gate. So this is my input, and this is my out. I could have something that's just like, a black line that's just a step. You go like, when I get to a certain level, you're all on or you're all off. Heaviside step function, and it's got some threshold where you go, the only thing I'm free to move is like this guy backwards and forwards. So I choose where this offset is. Doesn't have to be at 0, it can be anywhere. That's like the logic stuff we were talking about with predicates last week. But maybe you want something a bit smoother. Maybe, you know, maybe there's values of truth in between. It's more like a probability where we're going to go some smooth function between 0 and 1. And the things we can choose are the slope of this guy and the offset. So we can shift this around and we can steepen it up or stretch it out. And that behaves a little bit like this. So in terms of the getting to the output side, this is in terms of this nonlinear function that applies to an output. So what we'd call is this is a single layer neural network. We can say, so now this is where we get a bit silly, where we're going to go, let's guess a function that looks like this. We choose anything. This is an activation function, and we're sort of free to choose what we want. There's lots of different choices in the literature. I'm going to show you logistic function, logit. I'll try, it's going to be hard. I won't write because my pen's really terrible on this one. It's something like 1 divided by 1 plus x, oh, sorry, exp. So that's e to the x. And what we're going to do is x is a vector. So there's lots of little components. So we're going to have an offset, first offset, plus a1 times x1 plus a2 times x2 plus dot, 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 dot. So hopefully you guys can understand that. Remember when I was drawing the neuron, I had all those little different inputs. So I'm going to do this weighted sum, a1, a2, of all the inputs. Got some bias that I threshold it by, and then I've got this exponential function. So these can be positive or negative, the contributions of these guys. That is, if we're doing this, you can interpret this output as probability that something is true. And if we do that, this turns into something called logistic regression. Has anyone ever heard of logistic regression before? Sometimes it comes up in other contexts and people don't quite understand that it's actually a single layer neural network. single layer neural network is logistic regression. They're the same thing. It's just interpretation that's different. So what we're trying to do with this, well, how would we use this thing? We could try and, I'm glad a lot of you have heard of it. It's good. Is that other courses or just from previous study? No answer. Another course, cool. Okay, you're all ahead. So we can use this logistic regression as a classifier. We have, let's say we've got some data. Keep doing this. Got some data. We've got two features. Okay, so this one we're going to say is height. Shouldn't use this pen for writing, sorry guys. So in this axis we've got height in meters, and this one we're going to go hair length in centimeters. And what we're going to try and do, we have two features. So in our neural network we've got two inputs, and we're going to try and work out if someone is male or female. So what you would expect, so this might not necessarily be zero, just for demonstration. If height's in meters, you'd expect for, I'm going to use, so if I do this guy, that means male. And if I do this color, oh, try again. Male, and then I'll go 10. I'll pick another color. Go green. So that would be female. Probably terrible colors, sorry guys. So what you would expect is that female samples would be usually on average, females are shorter, and on average they have longer hair. So you get some data down here. Just do lots of that. And for males, you know, it's not a clear cut, but usually they're taller and the hair's longer. So we're trying to work out the probability that someone is male given height and hair length. And again, this is a probability thing because you got people like me, I'm male, I'm tall, and I've got long hair. So classes bleed into one another. So you never get this whole thing of, like last time, about saying the logic programming. It's like logic doesn't always work in the real world. These classes bleed into one another. So what you're basically doing is you can think about this logistic regression as an inner product. So the inside bit, lost all the things I wrote. We're going P of X equals some activation function. And you've got an offset plus an inner product with X. So these are vectors this time. So you know when we were talking about the first one, there's a vector, a characteristic vector for maleness in terms of these features. It should be something like males point out that way. There's a little vector going that way. Try again. So you can work out, you know, worrying about matrix stuff from earlier on in the course. Similarity with a vector is like an inner product. The maleness vector would be pointing in that way, so usually taller and shorter hair. So if you put that in, that gives you a classifier. So the magic is, how do you choose B and A given the data, which is where you'll get to at the end of this course, or you might have been doing it in another course. Like, how do you actually learn? Learning in machine learning is basically all it ever is how do you get A and B that are sensible given data? And we can sort of heuristic one here as we go, well, again, if we talk about a decision surface, it's like anything on this side of the line is going to be more likely to be male, anything away from that line over here is more likely to be female. The shape of the decision surface depends on your model. Single layer one, I think you get a straight line. That's a really basic neural network. I'll show you an example. This might be a unmitigated disaster, but I'll show you an example of one I was playing with recently. This might screw up. No, I can't open the camera. Wait up. I have to show. Okay, so if I video. Now maybe I can share this with you. So let's see if this works. So this is a neural network called YOLO. Don't know if anyone's heard of this. Can anyone see my screen now? That person, that's me. It's running fairly slowly. You should be able to see if I hold up my phone. This is running on the CPU on my computer. Usually with neural networks, you run, sorry, I'll bring that in. So you can, I'm holding up my cell phone. Thinks my picture in the back is a clock. So this is running at about a frame a second. This is designed to be a fast neural network for doing image classification. So what I'm doing is, again, this thing's just a function. It's a more complicated function, but it takes the frames of my webcam and passes them through a neural network, and it gives these outputs. So the output's more complicated in this one. It's not a 1, 0. It's, I'll probably stop that now because I have this feeling it's going to go wrong. And I can get my video back on. Oh, I need to stop that. Sorry. I was worried this would kill Zoom if I tried to share my webcam. Yeah, so this is a network called YOLO, which is a really much more sophisticated one. I don't know which one I'm sharing with you now. So basically this, again, we're talking about composition of functions. What YOLO does is it takes an image. Actually, I can probably show you the architecture in the paper. I think I've got that open. Yeah, so here we go. Quite a funny dude, this guy, Joseph Redmond. After this, I'll quickly show you his CV because it's the funniest CV I've ever seen. What this does is it takes an image. So what I was doing in that demonstration is I take a frame from the webcam, pass it through the network, one at a time. So that's why it's slow, because it's running on the CPU on my computer. My laptop doesn't have a GPU. You do it as a GPU, then it runs at a high frame rate. What this guy, the architecture of this is, again, it's all this composition of functions. So you take the original image, you pass it through a particular type of linear operation called a convolution, and you do a thing to reduce the size called max pooling. Convolution max pool, convolution max pool. So little thing they're not saying down, 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 down until you get to this thing. So like you can think of like each one of these is like one of these single layer things. It's going like all of the image down to a pixel is one of those logistic regressions. So, you know, we had a vector, the size of the image would be, and a bias for each one of those. And there's one of those for every pixel. So when you're doing a deep neural network like this one, you can, in your head, how many weights do they have to do? It's a lot. So you're trying to fit millions and millions of weights, which are basically all they are. These things are this little vector going, that way's male, that way's female, this way's a cat, this way's a dog. And passing it down through this chain composition of functions. So when we're talking about function compositions, neural networks are all about composition of functions down till you get to the output layer. In this case for YOLO, what the output layer is are these bounding boxes. So it has 4 outputs, and they're the position from the top corner of the image down to the center of the box, and then how wide is it and how high is it, and the class. Maybe that's 5 outputs. basically what you do, and it gives the confidence for that. So there's nothing more sophisticated than that original example, logistic regression. Deep neural networks are just the same thing. It's not clear why you need so many layers. And the trick, all the magic is like, how do you get these things to learn those coefficients? But again, they're just functions. So they're, in this case, it's a multi-input, multi-dimensional input, multivariate input, multivariate output function. We were just talking about univariate input functions and single value multivariate functions in this course, but it's nothing more than that. So that's how YOLO is set up. Practically, if you want to look at it, I think I have VS Code open. Let's see if I can share my screen with you for this guy. So this one I did with OpenCV, and it's a pre-trained network. I didn't actually learn the weights. I downloaded them from this guy. He's run it on a, typically when you're doing neural networks, training takes a long time. Classification is fast. Again, you're trying to find all these magic numbers that go into the thing. So this thing is a config file for defining that network. This is the input one, and then you have a learning rate, blah, blah, blah. So these are the layers. You have these convolution layers, and you have an activation function. In this case, it's called leaky. So I was showing you a logistic activation function before. This one's got a thing called a leaky activation, which is a little bit magical. I can show you what that looks like if you're interested. It's a leaky activation function, looks like this. It's not going, you know, the ones before I was saying like, oh, it's like this dash thing, smooth thing. It's not like that. What it is a thing that goes up with a slope, and below here, a very shallow slope down here is the activation function they use. A little bit magic why this one works better than the other ones. I think the theory for that's still a little bit exotic and people haven't quite worked it out. If you want to make a career for yourself, do the theory and say why these activation, such and such an activation function is better than another one. It's a leaky ReLU. I'll write it in the chat. So what that is on the negative side, it's not zero. It's a small slope down from zero. That's what they mean by this leaky activation function. And you downsample, just a big chain of these things. So they're nothing more complicated than logistic regression. It's just a big composition of logistic regressions with some subsampling. That's all they are. Look how many there are. It's huge. It's a huge, huge model. Huge, huge, huge. That's why it's slow on CPU. Cool. That's it. I'll just quickly show you this guy's CV. If you ever want to apply for a job and you're really brave. Looks like I don't have it open. Oh, maybe it's here. Oh, no, I don't have it open. I'd encourage you to go on the internet, look at PJ Reddy's CV because it's hilarious. Joseph Redmond is the guy. Any questions about that? Any questions about anything while we're here? Nothing? Everybody's happy? So I'm a little bit sad. This will be my last lecture for you guys. You're moving on to Hamid's next, I think. Yeah, so we'll do the quiz in 2 weeks. I think that's the last time I'll have you guys. You'll move on to more, so you'll go deeper and deeper into the calculus side of this. So by the end of that, you should have all the equipment you need to really understand these results, so state-of-the-art results. So like this one. So this was only, but in neural network times, it's quite a long time ago. 2016 was when this one got uploaded. I was actually working with neural networks at this time for remote sensing, and this came out and I'm like, oh, that's cool. It's really fast. It's not quite what I needed though. Bounding boxes aren't quite what you need often. So output depends. I ended up using a different architecture called a UNet, which was really useful. Yeah, so if no one's got any questions, I'll say good night. Thank you for turning up. Sorry for the drama with the link at the start of the lecture. It's recorded, so hopefully everyone will be able to see it. Okay. See you guys.